to go. We're almost there. Yeah, you've almost done this. All right. Next is going to be maximum likelihood. Last is going to be Bayesian inference. Yeah. And they both have problems, but they're both considered generally better than some of the other things that we have gone through earlier. They're more sophisticated methods that use a little more of the data than some of the others. So, maximum likelihood, general statistical model for estimating unknown parameters. So, like, whereas the other models assumed that if this is A and this is G, then there exists a point halfway between A and G, which, show me that in a chemistry lab. I'll be real impressed. Yeah. Pardon. But in this case, with maximum likelihood, we're going to estimate those parameters based on the sequence. So now we're a little more like the way that HHPRED goes about alignment, where we're aligning sort of groups of things to each other and inferring, based on various bits of data, what's the most likely path of evolution. And we're going to have some parameters. That's our other vocabulary words. So that's something about the model, generally a number that goes into the model or a constraint you put on the model. Like this is allowed to happen, this is not allowed to happen, something like that. Or when this happens, I give it a penalty of a certain thing. When this happens, I give my algorithm a reward, like a little cookie or like a point, a little bonus point. Yeah. So, all right. So for example, consider a normal distribution, like a bell curve, of a population with two parameters, the mean and the variance. So the mean is going to be bam right there. The variance is going to be how widely the data is distributed around the mean. And there are going to be different ways that we can calculate that. We could calculate a standard deviation. Variance is actually a thing that can be calculated. There are statistical methods for deciding, how much of the curve should we take into account when comparing different curves and different means. So there's different schools of thought on how to do this. But in general, we're using more data, and more data is better when we can do it. So, in phylogenetics, the parameters could be different rates of evolution. We could say, no, we know these things are going to have similar rates of evolution based on experiments in a laboratory, based on observation, something like that. Or we can say, we know they're going to have different ones because, people have babies every 20, 25 years, something, and then don't have any more babies. Yeah. Whereas bacteria have babies every certain number of minutes, 90 minutes or something. Yeah, ridiculous. Different transformation costs. So the difference between like a transition and a transversion. One might be riskier, costlier, something like that. A change that knocks out a conserved cysteine and a zinc finger might be heavily penalized by evolution, whereas a change of the base next to it doesn't really matter. It's just really a spacer, and so that would be less punished. And the tree itself would be considered a parameter in this. Okay. So likelihood is proportionate to probability that the data fit the model, basically. It's just a statistical way of getting it out there on paper. So we're going to call basically the fit between reality and between your data and this model. That'll be called the likelihood. We're going to model likelihood as a function, and we're not going to do this with math. We're just going to conceptually say there's some combination of operators, x squared minus 2x plus y, whatever. There's going to be a way to maximize likelihood. And then we're just going to look for where does this likelihood function have the highest level. That's what the programs are doing. So they're looking for what is the best fit of tree to data given what we know about how evolution works. So really, for the first time in all of these methods, we're taking what we know about evolution and putting it into the hopper to help out with the calculation. Okay, and so people will abbreviate this. They'll say it's an ML tree, maximum likelihood. That's fine. We're going to determine tree topology, how the branches join together, and branch lengths, all of those things. And we're going to find what length and what topology has the greatest likelihood of being produced from a data set. Problem is, these methods take in more data is taken into account, but that means it takes longer to actually run the method. So it's a really good way to do it when you have enough data to be able to do a good job with it. And if you have too much data, this may not work. If there are large amounts of evolutionary change and you can't tell what should be lined up with what, then maximum parsimony may fail. But maximum likelihood will give you a statistical model for evolutionary change across the branches. So you can use it both ways. You can use your sequences to infer a tree where they join together. Or you can use your sequences to infer a tree that then tells you something about evolution. You can look at the parameters that come out of your tree and say, oh, wow, when I join these things together, the tree always looks like this, or the branch lengths are always this. And based on that, you can say, oh, wow, rose plants evolve faster than dandelion plants, or something like that. Yeah, some sort of conclusion like that. And so potentially you can get a look under the hood, look at what happened in evolution, and make conclusions about how we got here to this point. And I think for a lot of people, that's why they're interested in phylogenetics. They want to answer that question. What happened before I was here? How did we get here? How did these things get the way they are? And yeah, it's a very powerful, interesting way to look at the world. And maximum likelihood methods are probably one of the best ways of doing that. So, you can use maximum likelihood to estimate which genes or positions within genes are under positive or negative selection. What's that mean? Positive selection means that you have a gene that, given whatever your environment is, gives you a little bit of a growth advantage, reproduction advantage, some kind of advantage that's going to lead to you leaving behind more offspring in the end. Negative selection is going to be something like a gene that gives you cancer, which is going to make it less likely that you will pass on that gene. And so eventually that gene probably dies out if the negative selection is strong enough and happens at the right time. Yeah. Something like Huntington's disease is inheritable, is horribly damaging, but because it usually only shows up at like age 45 or something, most people are already past the point where they have done all the reproducing they're going to do at that point. And so, because it doesn't show up until too late, you may have already passed it on to your kids before it shows up. Yeah. Which is kind of a bummer. Yeah, for everybody. Yeah. And nothing you can do about it. So that would be a case where something you would see is deleterious. It's like a bad gene for the health of the individual, but because it doesn't have an impact on reproduction, and may actually have the opposite impact, because before everything falls apart, Huntington's disease will often make people, it's correlated with more impulsive behavior. And impulsive behavior can lead to children. I've heard, yeah. And so you may actually end up spreading this bad gene more widely just because its effects happen to have this side effect that they spread themselves. So yeah. But anyway, you can calculate positive and negative selection of genes based on maximum likelihood models, which is neat, yeah. And we're not going to do that in this course. That's like a separate thing. That'll be like an advanced bioinformatics, like grad school level. But it can be done, yeah. And it's worth doing. The people that are good at this are highly sought after, and they have a lens on the world that the rest of us do not have. Yeah. When sequences evolve in a heterogeneous fashion, so there's a lot of evolution here and then not much for a while, and there's a lot of evolution here but then not much for a while, then more over here. So it's like, kind of random, which is probably the best model of evolution. So in those cases, maximum parsimony can beat maximum likelihood. But generally, maximum likelihood is going to give you more versatile data and better data if you can. So maximum likelihood, like the parsimony, will evaluate a bunch of different trees, possible trees. In the terms of maximum likelihood, we would call these hypotheses of how things are related, hypotheses of relationship. But it's going to consider the probability of each of those trees based on some model of evolution, like A will usually change to G but rarely change to C or T, something like that. And based on that, if that assumption is good and holds true, then you may get a better tree with maximum likelihood, because you can calculate what are the odds that this thing would happen. Yeah. And then the tree that has the highest probability value of explaining the data is going to be preferred over trees that have lower probability. And so that's the method, basically, in a nutshell. Easier to do on a computer than it is to conceptualize, I think. So it's going to be, let's say we're going to use it for molecular sequence data. So nucleotides, there we are. And so let's only look at the positions where the bases differ, because all the rest of those, remember, are uninformative. They just help us to identify the things that have changed. And then it's the things that have changed that are the basis of this analysis. So let's imagine there are a bunch of possible trees. In this case, let's imagine there are 3 possible trees that connect these sequences up. Maximum likelihood is going to evaluate each possible tree and calculate for each character, like character being like base 43, 58, or 90, the total probability that each node on the tree possesses a particular nucleotide. So it's going to make a tree and going to say that, okay, what's the probability that base 2 is going to be an A? Or, sorry, base 58 is going to be an A. The answer is it's 0.75 probability. So it's going to store, instead of storing a sequence, which is just going to be A, we'll assume it's A, which may be wrong, but that's what we did in the maximum parsimony model. We're going to say it's 75% A and 25% T. Great. And then we're going to say, what are the odds that we could change from an A to a T? Or change from an A and a T to a G or a C, something like that. What are the odds at every step? So you're going to add all these probabilities together and get a probability for the entire tree. You're going to make lots of different trees and compute the total probability for each tree. And then the tree with the highest overall probability is going to be preferred over the others. Yeah. And it may be really close to the second best tree, or it may be really far from the second best tree. And so really careful people will look at the probability of the 10 best trees, 100 best trees, something like that, and give you a sense of how often this particular branching topology is represented in those sequences. So yeah, I think we'll pause this video and then we'll come back and do the last little step of this one, maximum likelihood.